You know, if I were smart, I'd probably write up the homework problems for you and do them as well. But I'm not. And so instead, I'm going to do some more footprint problems before we move on to today's topic, which is disks and washers. We're doing rotational volumes today after we warm up with a little practice with footprints again. So we're talking about footprints here. And I thought we could use 4 minus x squared as our region for all of these problems. So this is 2 and this is 4. And I want to envision drawing different things on these regions. Okay, so let's think about this. Oh, and of course bounded from 0 to 2. Let's make squares. So if I'm making a square here, that's the side of the square. And the square comes up, and this is the top of the square. Well, the side of the square is this distance, and we know that this distance is called y. So if I'm thinking about integrating from 0 to 2, the side length squared, and the thickness here is measured on the x-axis, so this is a dx integral. What's my side length? Well, the side length is y, so I would have y squared dx. Well, I need to have everything in terms of x's for this integral. So I'm going to have to get rid of y and replace it with what y was equal to. Remember, y is equal to 4 minus x squared. So this will be the integral from 0 to 2 of 4 minus x squared. That's the side length squared, right? Because this is y, and we need y squared dx. Okay, so there's my integral for squares. What about semicircles? Well, there's two types of semicircles that we can look at. 2, 4. Let's look at one where the diameter is this length. So these are the semicircles that we're talking about. Again, the thickness of each of these slices would be measured on the x-axis, so it's a dx integral we've got. And again, we're integrating from 0 to 2. And again, we're integrating the area. Well, these are semicircles, and so we want pi r squared divided by 2 dx. So what's our radius in this picture? Well, I know that the diameter in the picture is my y value. And radius is diameter divided by 2. So radius must be y over 2. And our y value, remember, was 4 minus x squared. So that's the radius. That's what I'm plugging in there. See these? These are constants. I'm going to take those out. And so I'm going to have here pi over 2 integral 0 to 2 of 4 minus x squared over 2. And don't forget the radius. This has to be squared. Now when I square that bottom, I'm going to have 4, and I'm going to pull that out, and I'll have pi over 8 integral from 0 to 2 of 16 minus 8x squared plus x to the 4th dx. I'm not bothering to integrate these because I think the challenge isn't in the integrating of this. I think the challenge is in the setting this up. So I thought we could focus on setting up. I said there were two semicircles to look at. That was one of them. The other semicircle we could consider is this semicircle. 2, 4, where the radius is in the plane. That's much larger, isn't it? So radius is now our y value. And if we want to integrate pi r squared over 2, because we want half of the area of a circle from 0 to 2, dx, we're going to replace radius with y. And what was y equal to? 4 minus x squared. So pull out the constant, 0 to 2, and 4 minus x squared squared is dx. Pi r squared is the area of the circle. That 2 is not being squared, so I can pull it out as a constant now. Okay, this is similar to the last one, but a little different. Notice I just have a pi over 2 in front. I'm going to end up with the same 0 to 2, 16 minus 8x squared plus x to the 4th dx that I had last time. And again, that's a very simple antiderivative for us to find, so I'm not going to wait on it. What would be the difference if you were integrating circles? Cross sections are circles. Well, instead of adding up a bunch of pi r squareds over 2, we're just going to add up from 0 to 2 pi r squareds. And our radius here is our y value. R equals y equals 4 minus x squared. And so we get pi 4 minus x squared squared because radius is squared. I can't tell you how many people forget that squaring over here, especially if there's a squaring there. They say, oh, I'm all done. And they're not all done. So watch out for that from 0 to 2. Okay. We could look at some triangles. That might be good. How about we have our region, and this time we make a triangle whose height, a right triangle, whose height is twice, 2 times the base length. Here's our base length. Here's our height. Maybe if I draw it here. Base length, height. Okay, and this is a right triangle so that we could actually use our base 1/2 base times height formula. So we know that the base is our y value, and the height we said was 2 times the base, or 2y, and the formula for area of a triangle is 1/2 base times height, or in our case, 1/2 y times 2y, or y squared. So I'm integrating y squared dx from 0 to 2. What was our y equal to? 4 minus x squared. Don't forget the squaring. Dx from 0 to 2. You know, I was just thinking that maybe we should consider not just dx integrals. What if we had this? What if we had squares going this way? Now my side length is x. But now the thickness of the slice is measured on the y-axis. So I want side length squared, but this is a dy. And I'm not going from 0 to 2 anymore. I'm adding up all the slices that go from down here, squares, to up here. So I'm going from 0 to 4. And I need y equals. Okay, we know y equals 4 minus x squared. So let's get everything written in terms of y. I will have x squared equals 4 minus y. and x equals square root of 4 minus y. Why don't I have to worry about the plus and minus here? Well, let's think about what this would be if we had the plus and minus. It would be this sideways parabola, and we don't have this bottom part. We only have the top part, so we're only looking at positive. So x is equal to the square root of 4 minus y. Okay, remember we said we were integrating area here, and the area of a square is side length squared. And so for us, the side length we said was x, which now we understand is square root of 4 minus y. So I'd be integrating from 0 to 4 square root of 4 minus y squared dy. That might bear doing, huh? So let's see what happens. Oh, but wait, squaring a square root, that's not a problem. I just get 0 to 4 of 4 minus y dy. Well, that's going to be 4y minus y squared over 2 from 0 to 4, which is 16 minus 16 over 2, 8, and I get 8 as the volume, 8 units cubed. Now, some people wonder if this, well, Mr. Kukla, why couldn't I just do it with squares the regular way and not worry? Well, let's take a look at that situation. So if I were to integrate squares this way, so there's my side length again. So we're integrating y squared dx this time from 0 to 2. And we said that y was equal to 4 minus x squared dx from 0 to 2. And so this is the integral from 0 to 2 of 16 minus 8x squared plus x to the 4th dx. So that's 16x minus 8 thirds x to the 3rd plus x to the 5th over 5. And I'm going from 0 to 2. So if I plug in a 2, I get 32. And if I plug in a 2, 2 to the 3rd is 8. 8 times 8 is 64 thirds. And if I plug in a 2, I get 32 fifths. Huh. So that's going to end up being 8, is it? Well, let's multiply everything by, make a common denominator of 15ths. So 32 times 15, 0, carry the 1, 16, 2, 3, 500, or, yeah, 500, minus 5 times 64 is 320, plus 3 times this one is 96. So we've got 180 plus 96 is 276 divided by 15. Is that 8? No, it isn't. So, you know, just because I'm doing squares, squares dx and squares dy, they're not the same thing. And AP likes occasionally, usually they do a dx integral for area. Sometimes they do dy, and so you need to be comfortable with that, or at least, you know, able to see it. It's not any different or harder math. It's just conceptually visualizing it. So let's do one more of those. Let's do semicircles this way. This is 2, this is 4, and here's my radius. Oh, and I only want a semicircle. All right, we'll do circles. So I'm integrating pi r squared dy. dy because the thickness of this slice is measured on the y-axis. Little y-axis measuring. Okay. And we're integrating from 0 to 4. Remember, our radius was x, and x was equal to the square root of 4 minus y. So I'm integrating from 0 to 4. I take out my constant. I have square root of 4 minus y squared dy. Pi pi, 0 to 4, 4 minus y dy. Well, we've seen that movie before, haven't we? That's going to be 4y minus y squared over 2 from 0 to 4. Don't forget this pi times pi. So pi, 16 minus 16 over 2, I have a volume of 8 pi units cubed. Okay, so there's a little review of footprints for you, and I don't think anything's going to help except doing a hell of a lot of them. No, really. All right, let's move on now to today's topic, which is rotational volumes. So I want to take a curve like y equals square root of x, and I want to rotate it about, and this is going to be important because sometimes we'll be rotating about x-axis or y-axis, or x equals 3 or y equals -2. We won't be rotating around anything diagonal. That's a Calc 3 topic. Let's just start with rotating about the x-axis. Okay? So what am I looking at? I'm looking at this situation. And let's integrate from 0 to 4, so we have this nice ordered pair, 4, 2 to work with. Okay? So if I'm spinning this region around the x-axis, this piece will come around, this piece will come around, this piece will come around, and I don't know if you noticed, but it's kind of looking like the last problem we did, where we were integrating a bunch of circles. Okay, so I'm thinking that if I'm integrating circles, I'm thinking about integrating pi r squared. Again, if I slice through this, I'll be slicing through with a dx thickness. I'm integrating from 0 to 4, but what's my radius? Well, the radius in this picture, though I've made it very hard to see, that's the radius. The radius is the y value, and the y value is square root of x. And we want pi r squared here. So we're going to pull out that constant, go 0 to 4 of square root of x squared dx. Talk about easy calculus. The antiderivative of x dx. So x squared over 2 from 0 to 4, don't forget the pi, 16 over 2, or 8 pi, not pi squared, units squared, cubed, volume. All right, so we can rotate not just around the x-axis, though. What about rotating about a different line, like the y-axis? What happens when we take this same region, 4, 4, 2, and we take this region and we spin it around the y-axis? Well, oops. When I do that, I'm going to get this, and I'm going to get this. I'm going to get a disk. Now, do you remember the formula for area of a circular disk, also known as an annulus? It's got an inner radius of little r and an outer radius of big R, and it's the area of the big circle minus the area of the little circle. That's the formula that we're integrating. So we'd be integrating pi big R squared minus little r squared. And notice the thickness. The thickness of these slices would be measured across the y-axis. So I'm not going from 0 to 4 anymore. I'm going from 0 to 2. All right, so what's the big R and what's the little r? Well, let's come back to this picture. If I look at the picture here, it looks like this distance is my little r. And that, we said earlier, was an x value, right? At this ordered pair, this would be the y value, this would be the x value. So this horizontal distance is x. If I drew a different washer, not at that place, but somewhere else, up here, for example, it would be much wider and much less material. If I drew down here, it would be very narrow. Well, one of the things I notice wherever I draw my washer is that this inner radius is changing. Little r is based on my x value. My x value here, my x value here. Little r is the x value. Big R, however, big R seems to be remaining constant. I seem to have a cylinder here. Big R is always this distance. Well, what is that horizontal distance? It's constant, it's fixed, it's 4. Big R is 4. And so then this integral would be pi 0 to 2 4 squared minus x squared dy. But wait a minute, I don't want to know what x equals. I want to know everything in terms of y. So we're using the region y equals square root of x. So if I square both sides, x equals y squared. So I'm putting a y squared in there and then squaring it. So I'll have pi 0 to 2, 16 minus y squared squared dy. Or pi 0 to 2, 16 minus y to the 4th dy. It's going to be a very easy integral to do. The hard part is in identifying my little r and my big R. And I want to give you some tips on drawing these that will help you, because if you can draw them successfully, then you can better identify radius, little radius or big radius, or just the radius of the circular disc. Let's go back to that first problem we did. Square root of x from 0 to 4. And I wanted to rotate around the x-axis. So when I do a disc or a washer, I draw a segment in the region perpendicular to the axis of rotation. So I draw a segment perpendicular to the axis of rotation. Okay? And then at each end of this segment, draw a circle whose center is the axis of rotation. This is the axis of rotation. This is what I'm rotating about. They told me in the problem I wanted to rotate about the x-axis. So I'm going to imagine that's the center of my circle there. And I'm going to take this endpoint and draw it as though I were drawing a circle whose center was the axis of rotation. So again, I draw a segment perpendicular to the axis of rotation, and at each end, but Mr. Kukla, you didn't do each end. Well, yes, I did, because here, this endpoint is on the axis of rotation, and so I only generate one circle. Same thing happens out here. I could do this, and then rotate that around. Note here, this is that thickness of the slice I was talking about. And if I were measuring that thickness, notice that thickness would be here across the x-axis. That's a dx integral. Okay? This is the radius of the circle. This is my y value at that point. This would be the x value. The radius of the circle is formed by the y value, or square root of x. Okay? So again, when you're doing a disc or a washer, you draw a segment in the region perpendicular to the axis of rotation, and then at the end of that segment, you draw a circle whose center is the axis of rotation. Now, why did I say circles at each end? Well, let's take a look at our second problem. Our second problem, remember, was when I took this region and I wanted to rotate it around the y-axis. So what we know now is I'm supposed to draw a segment in this region perpendicular to the axis of rotation. So if I continued this, I would be perpendicular. At each end of this segment, draw a circle whose center is the axis of rotation. There's my little r. And there's my big R. It doesn't matter where I am. Here, little r got bigger. Big R stayed the same. Okay? There is a place, so I make this is a washer shape here that I'm finding the area of. Remember, we're integrating area because when we integrate area times the dy thickness, this is inches squared times the thickness in inches. This dy is providing the height. We're actually finding the volume of not a flat disk, but instead a cylinder with a hole cut out. That's what this is. We're just going to make this dy head to 0. So we're going to stack up an infinite number of these, and we can get an infinite number if you let the height of each one head to 0. So we're integrating area, and the area of this shape we said was pi big R squared minus pi little r squared. In this problem, little r is my x value, which is y squared, and my big R, that's this distance, is a constant 4. So I'm integrating 16 pi, integrating 16 pi minus pi y to the 4th dy. That shouldn't be so hard for us at this point. 0 to 2, yes. I would pull out the pi constant. Okay, so let's rotate around some more things, because, you know, it's not just all about the x and y axis. Why not rotate about y equals 2 while we're at it? So we've got this region, and this is the point 4, 2, and this is my axis of rotation here at y equals 2. So remember what I said, when you're doing a disc or a washer, you draw something perpendicular in the region perpendicular to the axis of rotation. If I extended this, that would be perpendicular to the axis of rotation. Then, at each end, you draw a circle. You don't like that one? Draw another one. At each end, draw a circle whose center is the axis of rotation. Now what I notice here is these are on the same line. That means big R is a constant. But how big a constant? Well, this is big R. What's that distance? It's the distance from 2 to 0, or 2. Big R equals 2. What about little r? What's little r in this picture? Little r is this distance. Yeah, I'm going to draw it again. So, axis of rotation. And there's little r. Well, remember before we said that this was an xy ordered pair? And that this amount was x and that this amount was y? Well, we know that this distance is 2. And we know that this distance is y. So radius, this distance, let's switch colors. This distance is 2 minus y. So little r equals 2 minus y. And our y value, well, that's just y. But wait a minute. What's the integral going to be? Is this a dx or a dy? Well, if we measure the thickness of these slices, these are dx slices. So I don't want my information in terms of y. I need in terms of x. Okay, so the integral then would look like pi big R squared minus little r squared. Please be careful. I would FOIL this out first before integrating. Don't combine these stupidly. This is being squared, this has to be FOILed, and we're going back to 0 to 4. Because we're integrating this way. We have all these slices that we're doing. We're making all these and then we've got this up here. So what does that look like? Kind of looks like a strange vase to me on its side. The circular hole at the top gets narrower and narrower like a funnel, except it's a funnel inside a cylinder. Okay, there's that one. That was about y equals 2. What if we rotate about y equals 4? How does that change things? Yeah, I think I want to redraw this a little lower. So we know that this is 4, 2. We know that this is y equals 4. We're spinning it around y equals 4. We draw something perpendicular to the axis of rotation, right? We want to be perpendicular to that axis. And at each end, we draw a circle whose center is the axis of rotation. So, what can we say here? Well, again, like we saw in the last problem, my big R is constant. It's not changing. Big R equals 4. Okay? Now, what about little r? Well, little r isn't the same as it was. I mean, it is, but it isn't. So there's little r. This is still y. This is now 4. So little r is 4 minus y. And remember, y was square root of x. So my integral will be pi 0 to 4 big R squared minus little r squared dx. Okey-doke. How about this one? How about we rotate about x equals 4? So this is x equals 4, and I want to spin around that. If I'm spinning around x equals 4, remember, I want to draw something perpendicular to the axis of rotation. That's this. And at the end of that segment, I draw a circle whose center is the axis of rotation. Now, this is my radius, and I've just got a circular disk. Well, we know from before that this distance is called x, just like this distance is called y. This distance is 4. So my little radius here is 4 minus x. Little r equals 4 minus x. Does this have a big R? No, no big R, because look, I couldn't draw a circle on this end. Whenever our region, and by region I mean square root of x in this case, whenever our region lines up along an axis of rotation, we end up with not a washer, but a circular disk. If, however, there's a gap between our region and what we're rotating it about, then I end up with a washer. So if my region lines up along the axis of rotation, I get a disk. If there's a gap between my region and the axis of rotation, that produces this washer shape. Here, there's no gap between the region and the axis of rotation. Okay, so I've got a little r, and I'm integrating area. Pi r squared dy. The thickness of this slice would be measured over here on the y-axis. And so I'm integrating from 0 to 2. And we put our radius in here, and we whimper, because pi 0 to 2, 4 minus x squared dy. We need to have everything in terms of y's. Remember, ours was y equals square root of x, so x was equal to y squared. So my final integral would be 0 to 2 times pi of 4 minus y squared dy. Please remember to FOIL this out and don't just apply the squaring. That'll make the problem wrong. Okay, let's do one more. We did about x equals 4. What about x equals 6? Here's my region. There's 4. I want to rotate about x equals 6. So there's a gap between my region and the axis of rotation. I'm expecting a washer here. I draw something perpendicular to the axis of rotation, and at each end I draw a circle whose center is the axis of rotation. Notice the thickness of this slice would be measured along the y-axis. So this is a dy integral. Okay? Now, what can we say here? Well, my little radius, well, I kind of want you to notice it, so I'm going to draw the picture again. If I drew this, this would be my little radius. But if I drew this, this would be my little radius. And if I drew this, this would be my little radius. What do you notice? It looks like the little radius is a constant, and that constant is 6 minus 4, or 2. Now, what about the other end of that segment? That's a terrible circle, Mr. Kukla. I wish I had an undo button. Oh, I'm just going to redraw the whole damn thing. Sorry. Okay. But this time I only need to focus on the outers. Does this quantity change as I go up? Well, if I were down here, I'd have a much bigger circle than I do up here. This is my big radius. This is my big radius. So how can we figure out what big radius is? Well, remember, there's this value here called xy. This distance is x. This distance is 6. So big radius must be 6 minus x. Or in our problem, since x equals y squared, big radius is 6 minus y squared. So when I integrate, I'll be integrating from 0 to 2, pulling out that pi constant. Big R, 6 minus y squared, squared, oh my god, I can't tell you how many people forget that one, minus little r squared dy. Okay, so now you have a sense of why we're spending 6 days on this topic. Again, I draw in the region something perpendicular to the axis of rotation, and at each end of that segment, I draw a circle whose center is the axis of rotation. That helps me draw the picture. I also need to identify big R's and little r's along the way. Please remember that this point, wherever we draw it, if we draw it over here, this is still called x, this is still called y. If we draw it over here, this is still called x, this is still called y. You've known this since you were a small child. This isn't a new topic. It only feels completely alien and new. All right, tomorrow we will review discs and washers, and we'll talk about cylindrical shells. Cylindrical shells. All right, have a wonderful day, everyone.